started.
Okay, you have started, no? Okay. Yeah. So, what I am saying here, if there are variations in consumption expenditure across 100 households, part of the variation should be because of income, and part of the variations would remain uncaptured. If I am adding only one variable, one independent variable, that is income. So what can we say? We can say that total sum of square or total variations in Y in consumption expenditure in this example, it has two components. One component is explained by income and the other component is not explained, remained unexplained. The component that is explained by the regression model is known as explained sum of square. It is also known as regression sum of square. And the proportion that remains unexplained is known as residual sum of square. So, total variations in Y, that is the consumption expenditure, can be decomposed into one part that is explained and another part which is not explained. The explained part is known as explained sum of square and which is not explained is known as residual sum of square. Is it clear? Is it clear? Hello?
Yes, sir.
Now these are the two proofs that we need to do. But
so what is sum of square exactly? Like what are we summing up and squaring?
okay. Let me just go to that file. I think, does it have this diagram? No, it is perhaps in other file. Just I will check. Yeah. Just see this diagram. Suppose along the vertical axis we are measuring Y and along the horizontal axis we are measuring X. And this horizontal line basically represents Y bar. Okay. Now, corresponding to a particular value of X, this is the actual observation of YI. And suppose this is the sample regression function. Okay. So corresponding to this Xi, this is the observed YI. And this is the estimated line, the sample regression function. Now, if you see this, there is one vertical distance between the sample regression function and the actual YI. And then with respect to this average, I can get another vertical distance between the sample regression function and this average. Now, when I say variation or deviation, it is basically deviation from the arithmetic mean. So total variation of actual yi, observed yi from its arithmetic mean here, this total vertical distance can be decomposed into two components. One component is the deviation from the sample regression function, means yi, deviating from the sample regression function, that is y hat I. Another is y hat I deviating from y bar. So if I take this total deviation from the arithmetic mean, it has two components. One is the deviation between actual y or observed y and estimated y. Another is the deviation between estimated y and the arithmetic mean of y. So I am writing here yi minus y bar is equal to y hat I by y bar minus y bar, and another one is this yi minus y hat I. Remember, out of this total deviation from the mean, the estimated regression line, the estimated regression model captures basically this segment. This segment is captured by the estimated regression line. And this segment is not captured by the estimated line because the estimated line passes through this point y hat I. So if you see this total deviation, partly it is explained by the line, partly it is not explained, which is the residual, this yi minus y hat I. Now, if I just take square of both the sides and then summation, then what am I getting? What I am getting basically, summation of yi minus y bar whole square is equal to summation of y hat I minus y bar whole square plus summation of y hat I minus y bar plus u hat I whole square, and this can be decomposed as or rewritten as, this is nothing but what? A plus b whole square. So a square plus b square plus 2ab. Now what will be your 2ab? What will be the 2ab? 2 into summation of y hat I minus y bar into u hat I. Now from this graph itself, mathematical also we can prove. But from the graph itself you can see these two are actually mutually exclusive. This u hat I and y hat I minus y bar, these two are mutually exclusive. There is no overlapping between the two. So this 2ab component would be 0. You can prove it mathematically also. You can just go for expansion of summation of y hat I minus y bar into u hat I. Just mathematical simplification will give it 0. Because if you just multiply this by u hat I, then you are getting summation of y hat I into u hat I. And already we have proved that summation of u hat I into y hat I, sorry, not here, here, that is equal to 0. You see that is equal to 0. Already we have proved this, that this is equal to 0. And second one is, the other component would be y bar into summation of u hat I. And again we have proved that summation of u hat I is equal to 0. So the 2ab component would be equal to 0. Because these two segments are disjoint, mutually disjoint. So what I am getting? This total variation in y with respect to y bar. So for every yi you will be getting a corresponding deviation. So for yi this is what? Similarly you will get for yj like that. So for every yi you will be getting a deviation from the respective, from the arithmetic mean, that is y bar. And if you just square and sum them up, then that will basically give me total deviation, total variation. And this total variation has two components. Part of the variation which is explained by the model, by this sample regression function, and part of the variation that remains uncaptured, this part. Here I have done it with respect to a particular value xi, particular observation xi. You can do it for this, actually it is to be done for the entire space, entire set of observations. And then when you sum it up, you basically get TSS as the sum of ESS and RSS. Is it clear?
Yes, sir, understood.
So what would be your conclusion on this basic relationship? What would you like to conclude? Don't you think higher the ESS, better is the model? Isn't it? Higher the ESS means what?
Lower is the residual.
Yeah. Higher the ESS means larger part of the estimated model is explained and less of it remains unexplained. That's why I was telling, and I think Abhinav was also talking about that higher the R square value. Why we say higher the R square value, better is the model. The R square, how do I get R square? Basically this proportion ESS divided by TSS. So higher the R square value means larger portion of the variation in Y is actually explained by the estimated model. And smaller portion remains unexplained. That is why, in general, we look at a regression model that has high R square value. The reason is here only. Higher R square value actually indicates that larger proportion of variations in Y is explained by the estimated model. The example that I was citing here, it basically means, so for example, R square value is 0.7. Say dependent variable is consumption. Independent variable is income. R square value is 0.7. It indicates 70% of variations in consumption expenditure across the households. It is because of variations in income. Or I can say 70% of variations in consumption expenditure across the households can be explained by variations in income. Is it okay? Is it okay up to this point?
Yes, sir.
Okay, I'll again stop for a while and I'll take your reaction. I mean, how it is going on.